Hello students, Standard 12, Chapter number 1, Relation and Functions. Today we will discuss some examples of this chapter. Example number 1. Let A be the set of all students of a boys in a school. Show that the relation R in A given R equals to A, comma B, A is a sister of B, is the empty relation and R dash equals to a comma b, the difference between heights of a and b is less than 3 meters is the universal relation. Solution is, since the school is boys school, no students of the school can be sister of any students of the school. Hence R equals to 5, it means this is the null set, showing that R is the empty relation. It is also obvious that the difference between heights of any two students of the school has to be less than 3 meters. This shows that R dash equals to A cross A is the universal relation. Example number 2. Let T be the set of all triangles in a plane with R a relation in T given by R equals to T1 comma T2, where T1 is congruent to T2. Show that R is an equivalence relation. As we know that we have to show that in relation R is reflexive, transitive and symmetric. Here first R is reflexive since every triangle is congruent to itself. Further, T1 comma T2 belongs to R and T1 is congruent to T2 implies that T2 is congruent to T1. That's why T2 and T1 belongs to R, hence R is symmetric. Moreover, T1, T2 and T2, T3 belongs to R implies that T1 is congruent to T2 and T2 is congruent to T3 implies that T1 is congruent to T3. Hence T1, T3 belongs to R. Therefore, R is an equivalence relation. Example number 3. Let L be the set of all lines in a plane and R be the relation in L defined as R equals to L1, L2. L1 is perpendicular to L2. Show that R is symmetric but neither reflexive nor transitive. Solution is R is not reflexive. As a line L1 cannot be perpendicular to itself, that is L1, L2, L1 does not belongs to R and R is symmetric as L1, L2 belongs to R. Hence L1 is perpendicular to L2 and L2 is perpendicular to L1 as we can show in this figure. L2 and L1 belongs to R. R is not transitive. Indeed, if L1 is perpendicular to L2 and L2 is perpendicular to L3, then L1 can never be perpendicular to L3. In fact, L1 is parallel to L3. That is, L1 and L2 belongs to R and L2 and L3 belongs to R. But L1 and L2 does not belongs to R. Example number 4. Show that the relation R in the set 1, 2, 3 given by R equals to 1, 1, 2, 2, 3, 3. 1, 2, 2, 3 is reflexive but neither symmetric nor transitive. R is reflexive since 1, 1, 2, 2 and 3, 3 lie in R as we can see in the relation R. Also R is not symmetric as 1, 2 belongs to R but 2, 1 is not belongs to R. Similarly, R is not transitive as we can see in this relation. 1, 2 belongs to R and 2, 3 belongs to R but 1, 3 does not belongs to R. Example number 5. Show that the relation R in the set Z of integers given by R equals to A, B 2 divides A minus B is an equivalence relation. Solution is R is reflexive as we know that 2 divides A minus A for all as A belongs to Z. Further, if A, B belongs to R, then 2 divides A minus B, therefore 2 divides B minus A, hence B, A belongs to R, which shows that R is symmetric. Similarly, if A, B belongs to R and B, C belongs to R, then A minus B and B minus C are divisible by 2. Now a minus c equals to a minus b plus b minus c is even, because as we know that if we open this bracket, plus b and minus b will be cancelled and a minus c. So a minus c is divisible by 2. This shows that R is transitive, thus R is an equivalence relation in Z. Next, example number 6 is, let R be the relation defined in the set A equals to 1, 2, 3, 4, 5, 6, 7. By A R equals to A comma B, both A and B are either odd or even. Show that R is an equivalence relation. Further, show that all the elements of the subset 1, 3, 5, 7 are related to each other, and all the elements of the subset 2, 4, 6 are related to each other, but no element of the subset 1, 3, 5, 7 is related to any element of the subset 2, 4, 6. Solution is, given any element A in A, both A and A must be either odd or even, so that A comma A belongs to R. Further, order pair of A comma B belongs to R implies both A and B must be either odd or even, implies that B and A belongs to R. Similarly, AB belongs to R and BC belongs to R implies that all elements ABC must be either even or odd simultaneously, implies that AC belongs to R, hence R is an equivalence relation. Further, all the elements of 1, 3, 5, 7 are related to each other, as all the elements of this subset are odd. Similarly, all the elements of the subset 2, 4, 6 are related to each other, as all of them are even. Also, no element of the subset 1, 3, 5, 7 can be related to any element 2, 4, 6, as elements of 1, 3, 5, 7 are odd, while elements of 2, 4, 6 are even. For basic fundamental concepts of chapter number 1, please watch my previous video.